we take this term x inverse k, little k belongs to your kernel x, and we have to show that if this thing here belongs to the kernel, what that means is that this term here, this triple x inverse kx, that means it maps to the unit here, right? If this belongs to the kernel, it will map to this point, definition of kernel, right? So we now need to show that that's the case, that when we f it, when we map it, that f of x inverse kx is equal to the unit here of h. So that's to prove normality, to prove that the kernel is normal, normal subgroup. We have to show this. That's what it boils down to. All right. So let's try to show that. So it's up here. So f of x inverse kx. Now f is a homomorphic function. Remember. So we can split this up. Now I actually skipped a step. Strictly speaking, f of mn equals f of m times f of n. Right? So I've just done it twice. I've skipped a step. I mean, if you really wanted to be a bit pedantic, you'd say this is. You can rewrite this as f of x inverse times f of kx, but you can rewrite f of kx as f of k times f of x. Well, I've just skipped a step and written it directly. Okay. Now, k is any member of your kernel, right? So when you map any member of a kernel, by definition, you will get the the unit of h, right? So you can rewrite this f of k here as just e of h, and this term, it's an element, belongs to h. Okay, so e of h is this term will just be this term. So you can forget about this. So this just becomes this. All right. Now again, f is homomorphic, so you can rewrite this in these terms. So that'd be like fm fn equals fmn in a sense, right? Now these cancel. They just give you the unit of G, right? These are elements of your group G. So they cancel and just give you E of G, the unit. But we know from what was it, theorem 61, that the unit in G maps under F maps to the unit in H. So f of EG is just EH. That's, where was that? Here, right? Here. Okay, so in summarizing, this equals this. That implies that this belongs to your kernel. Why? Well, because it maps to the unit of your H. It maps to that, right? Okay, so this belongs to your kernel, and that's what we needed to show that the kernel is in fact a normal subgroup. All right. Okay. Next thing is more a lead-in to the final theorem, but I've run out of whiteboard, so we'll have to do that in next session. So so this is a bit of a lead-in. Take two groups, G and H, and you're using a homomorphic function f here to map from G to H. And let's say we have a subset of G, a subgroup of G, call it S, right? And it will be one of the, in fact it's the first problem I'll treat in the problem solving session, that if you map that subgroup S here, if you map that into T, you can show proof that subset of H, called T, is in fact a group. It's a subgroup, right? So so if you map a subgroup of G, you will get T, which is a subgroup of H. That's you could call that a theorem if you like, but it's one of the exercises at the end of the chapter 18, and I'll actually show you how to do that, to prove it, in the problem-solving session. All right. So that's just a bit of a lead-in. I do notice the problems in the exercises at the end of the chapter for lecture 18. A lot of them are more theory, prove this type problems than just relatively simple calculations. They're more, you could almost bring in those questions, those exercises, as part of the theory section. It's the distinction between calculation type problems and the theory and the exercises. You could almost bring into the theory as part of the theory section. All right. Okay, now we have shown that the kernel is a normal subgroup. It's not just a subgroup, it's a normal subgroup. Now the example here at the top left, so we're talking about this, right, shows that the reverse is also true. Now, what does that mean? So we've shown here that the kernel is a normal subgroup. So what would the reverse be? That would say that a normal subgroup can be a kernel. Okay, you want me to say that again? Now here, we showed that a kernel is a normal subgroup. And this example here is showing the opposite, right? It's saying that a normal subgroup can be a kernel, right? Going the other way, right? So it's a result of in homomorphic theory, in fact, that every normal subgroup is the kernel of some homomorphic function. So every normal subgroup acts as a kernel. It's a kernel for some function f. That you can find some function f that makes every normal subgroup of G, okay, a kernel. Meaning that when you map it, you get the unit of H, right? And what is that mapping? Well, it was this one, right? That's how you do it. Here's your normal subgroup N, right? Normal subgroup, right? And how do you? So you map it using this formula. That f of x is just xn, and then what's your kernel? Well, it was n, right? So you're asking the question here, what's the unit of g of n? Here's your quotient group. What's its unit? Well, it's n, right? So if you map n, you'll get the unit of the that's what we showed here. The solutions y that such that f of y maps to the unit here. We found, remember this discussion, that those y's were in fact your normal subgroup. Okay, so your normal subgroup then is the kernel. So you can go from the normal subgroup, you can see that as a kernel for a particular homomorphic function, which is this one. Right? You take your normal subgroup and you make a coset out of it by using this formula. That's the recipe. That's how you do it. Right? Now, just to finish off, in the form of a question, which is like a lead-in to the next session. The next theory session, it's really just one theorem. So I think I'll I'll just make one session out of this next theorem, the last theorem, and combine it with the problem solving. So probably just do it all in one session. Okay, so the question is the following. So you're mapping with a homomorphic function f, as usual, from a group big G into a group big H, right? And you're told that two elements of G, just x and y, they map to the same element in H, call it little h, right? In other words, f of x and f of y map to the same h. In other words, f of x equals f of y, right? F of x equals f of y. If that's the case, and f is a homomorphic function, what does that tell you about x and y? What can you extract from that? What can you conclude about x and y? And that's like the question motivating the next theorem, which would be number, 63, right? I've run out of boards, so I'll stop here.